independent inhomogeneous bilinear interaction and the speed transfer torque. My topic contains these 4 parts. First, I will give an introduction about the background, and then I will introduce my work and the summary, and last I will give some open problems. About the background, in magnetic nanowires, self-organization is one of the most interesting phenomena in matter. In magnetism, this phenomenon has been intensively studied in terms of the spontaneous formation of magnetic domains, such as stripe domains, bubble domains, and the magnetic vortex. Many efforts have been devoted to the investigation about the dynamics of 3 types of magnetic excitation states in the ferromagnetic nanowires, namely spin wave, domain wall, and the dynamic solitons. The spin wave, domain wall, and the dissipative solitons can be triggered by the spin transfer torque. The spin transfer torque is drawn by the spin polarized current. Nowadays, the spin polarized current have been widely used to create, manipulate, and control the excitation of magnetic nanowires. The study of magnetic nanowires involves 2 important problems: the dynamic behavior of the system and the experiment management. In general, different research focuses lead to different model equations. The classical Landau-Lipski geometry equation, the equation 1, describes the dynamics of inhomogeneous one-dimensional ferromagnetic spin chain with Gilbert damping. Here, the second term, lambda s times HEFF, describes the damping. The change of magnetization vector due to the damping parameter, and lambda is the damping parameter. The first term of this equation describes the precession of magnetization vector of the effective field HEFF and the angular frequency. When the damping parameter lambda is positive, x tends toward the direction of HEFF and vice versa. When lambda equal to 0, the Landau-Lipski geometry equation 2 degenerates to the Heisenberg spin chain equation. In statistical physics, the Heisenberg spin chain equation describes spin-spin interaction of magnetism as a discrete one-dimensional model based on a variety of translits of the effective field, the HEFF. Landau-Lipski equation are studied by many physicists and mathematicians. When a spin-polarized current injects into the ferromagnet, the dynamics of localized magnetization is described by the modified equation with spin transfer torque. Here, Tb equal to gamma T s x describes the spin transfer torque resulted from the time-dependent spin-polarized current. Our model is this equation 3. We consider this generalized inhomogeneous spin chain equation, where we have took the effective field HEFF equal to alpha t plus beta tx times the sx, the differentiation of this equation. Time and size it represents the time and size dependent inhomogeneous bilinear interaction, and the last term, the time-dependent spin-polarized current. Here we have take gamma t times sx. It's caused by the spin transfer torque. So we just consider this model equation. From the point of we have these 3 main results. From the point of view of the moving space curve, equation 3 is equivalent to the generalized inhomogeneous nonlinear Schrödinger equation, this equation 4, and equation 3 is also sketch equivalent to the generalized inhomogeneous nonlinear Schrödinger equation. By virtue of this gauge equivalence, we can obtain the magnetic Soliton solutions of the spin chain equation 3. Because the equation 3 is nonlinear and it's very complex, so it's difficult to solve it. Because of this equivalence of equation 4, we can solve it. First, let's now give some details. First, let's give the last pair of equation 4 is the nonlinear Schrödinger equation. By using the INHOMOGENEOUS procedure, we obtain the last representation of equation 4 like this. The generalized nonlinear Schrödinger equation 4 can be yielded from the zero curvature condition of equation 5. Set the gauge equivalence. Now we introduce the gauge equivalence of these two equations. Set phi 1 and phi 2 be two linear independent eigenfunctions of phi for spectral parameter eta t, and denote the capital phi equal to phi 1 and phi 2 this matrix with 2 times 2 matrix, and we assume that it's invertible, which is also satisfies the linear problem phi. And set GST equal to capital phi with this invertible 2 times 2 matrix 1 eta t. The spectral parameter equal to 0. Take a transformation, this transformation 6. Then from phi, we obtain the last representation of the Heisenberg spin chain equation, the equation 3, which is reconsidered. Well, this is the last pair of the Heisenberg spin chain equation. At last, we can get the explicit magnetic Soliton solutions by using the double transformation. We started from the zero solution and obtain the one Soliton solution of the generalized nonlinear Schrödinger equation 4. Then we can get the eigenfunctions. And here we denote this is just some denotes. When eta equal to 0, we have this. Generally, we just need to get the GST, the matrix, and we need the eigenfunction. So we get phi 1 GST equal to phi 1 when eta t equal to 0. With the transformation 6, we obtain the spin vector of the equation 3 corresponding to the one Soliton solution of the generalized homogeneous nonlinear Schrödinger equation. This is the exactly magnetic Soliton solution of the Heisenberg spin chain equation 9. Finally, using math, using some figures, we analyze the solutions. Figure 1 shows that the damping and oscillation of the spin caused by the parameter beta t, and the black, red, and the blue curves on the black sphere describe the spin state of the spin chain at t equal to 1/2 and equal to 1 and 2 respectively. We can clearly see that when beta t equal to 1, it shows that with the time increasing, the trajectory curves shrink gradually, and when beta t is periodic, it's equal to 2 times sin t, it shows that with the time increasing, so the time from 1/2 to 2, the trajectory curves oscillate around the direction of S1. The second figure shows the damping-like effects and the oscillation of the spin components caused by beta t. The figure ABC shows when beta t equal to t. With time increasing, S1 induces to 1, and S2 induces to 0, S3 induces to 0 too. Beta T gives rise to a damping-like effect here. And in DEF, in the figure DEF, beta T is a time periodic function. The spin components oscillate with beta T. This also verifies the last result. The third figure shows the influences of the parameter beta T and gamma T to the dynamics of the magnetic solid given by the equation 9, the magnetic solid solution. In A, B, C, it has these parameters, and the beta T equal to 1 equal to 2p, and beta T equal to 2 times sin t, and gamma T is 0. Gamma T is 0. So gamma T is we just want to see how beta T influences the property of the magnetic solid solution. And in DEF, we just let beta T equal to 0 and gamma T changed to see what happened this time when gamma T changed the property of the magnetic solid solution. In summary, we have these conclusions. When beta T, the integral of beta T equals to infinity, the magnetic solid gives rise to damping. When beta T is periodic, the magnetic solid gives rise to oscillation. And the spin transfer torque gamma T change the property of the magnetic solid. And at last, when beta T equals to 0, the magnetic solid has conserved the quantity. And but when beta T is not equal to 0, the conserved quantity is break. At last, we give a summary. In this work, by establishing the gauge equivalence between the spin chain equation and an integrable generalized nonlinear linear equation, we present explicitly a novel non-autonomous magnetic solid solution for the spin chain equation. The results display how the precession frequency of the spin and the propagation velocity of the magnetic solid can be controlled by the bilinear interaction and the spin polarized current. Especially, we find out that the site-dependent bilinear interaction may break down conserved quantity and gives rise to damping-like effect in the spin evolution. Here we have some open problems. I just see how to find more explicit magnetic solutions to describe the spin wave domain and the dissipative solidness. Because the domain and the spin wave, these features are just important in the physics. And second, can we find the log waves of the spin chain equation using this equivalence? Since we don't, we have not yet do it from the non-zero seed solution to do this. It's very complicated to compute it. The third question is how about other model equations or coupled equations with spin transfer torque? Because when we think about different physical problems, the model equations are different, and there are many physical equations need to be solved. It's important to obtain its exactly solutions, and it's useful in the physics. Here we just consider one. Thank you.
I remember you mentioned at the beginning that it's related with the self-organization. Can you explain what's self-organization and how does this Soliton solution are related with that?
Self-organization. Self-organization is just induce the spin wave and some excitation in physics. And the Soliton solution is one of the excitation. No. I think self-organization just induces the drive to make and bubble theories that just like this, the excitation in physics. And the solid solution is one of the excitation.
Okay, thank you.